people often forget the idea is not to work harder, but to work smarter in engineering and have more time for innovation as a company. If you work smarter and you do exactly what is needed to fill up the high level goals, then you are not spending your time on over engineering and over analyzing. And then you release the product sooner, and you have time for other things. You have time to go to a technology conference or some supplier visit and gain more knowledge and enjoy your time in the company. So that's what I see. They keep forgetting what is the goal, you know.
Welcome to the Feria TechCast, where we bring you all things science, engineering, technology, and innovation. Today we are joined by Prachurya Bharadwaj, a capital equipment strategist whose career spans semiconductor lithography at ASML, wind turbine blade architecture at Siemens, and groundbreaking medical device development at Oxford Nanotechnologies. With experience across 4 countries and multiple high-tech industries, Prachurya specializes in answering the tough questions that keep engineering executives awake at night. Questions like, can this prototype actually scale? Where are the hidden bottlenecks in our system design? Or how do we transform brilliant technical concepts into commercially viable products? Our approach combines design for Six Sigma methodology with practical scaling framework that have helped startups and companies alike. So, Prachurya, welcome to the show.
Thank you, Ezekiel.
All right, so we'll dive into the interview. So, firstly, you have a strong practical background in mechanical engineering. So, how would you give a speech to high schoolers to make them understand what mechanical engineering is all about and to love the profession?
High schoolers, right? Okay.
Yeah.
All right. I would say mechanical engineering is magic in the purest form. Um, every structure that you see around you, any structure, it could be a rectangular shape, a cylindrical shape, spherical shape. These are all products. These are all thought processes of mechanical engineering. So mechanical engineering is nothing but manipulation of something called degrees of freedom. So in general, we have 6 degrees of freedom, which can also be expanded to 12, and that can be made into 24. So how do you make sure that a product is stable, completely stagnant? You just bound it completely in all the four directions, and sometimes the product has to move in this manner. So you just make sure that the y-axis is not constrained, but then the x and z are constrained. So things like that. That is one way of looking at how you can develop products. And that's the basics, to look at your degrees of freedom and therefore make various products. It's a little bit similar to making a sculpture or a painting, but instead you're manipulating physics, you're manipulating materials, you're manipulating doing calculations, and you have answers to why this will not move or why this will break down, or how many years will this product survive. So engineering in purest sense is absolute magic, if I'm talking to high schoolers, of course.
Wow, that's wonderful. I mean, if I was an high schooler hearing this about mechanical engineering for the first time, I'd definitely be convinced to take that path as my career choice.
I hope for that. I really hope that people don't give up on mechanical engineering, and because the world is going more and more towards data and LLMs, but I hope that this field continues.
Yeah, I do too. So, from having experience in oil rigs to nanotechnology. So, how did your 5-year nanotechnology degree shape how you approach large-scale engineering problems.
Honestly, it's a very good question. So the reason I went into large scale engineering projects or engineering roles, that was in Indian Oil, and that was because I was still a student in Central University of Jharkhand, India, and then I did started as an intern, and then they hired me, and then I continued being an actual engineer there, and they even like paid for my scholarship, and I went to South Korea and everything. So the reason I started with Indian Oil was because I was just interested in chemistry, in oil, in the overall processing, etc. But I was also interested in structures and making machines and making looking at the smallest chemistry, the smallest atom can make a significant difference in the overall system, in the overall structure. So because of that, I went towards Indian Oil. Also because they liked me and I continued. At that point, I was a child, right? So I was like, I liked it and they liked me, and I continued earning an extra income while I was a student. That was a bit of, to be honest, that was a little bit of a um, luck factor over there that I went to Indian Oil. But as soon as I finished my nanotechnology 5 years nanotechnology education, I did get very amazing chances in Oxford Nanopore because I was in South Korea. And I developed my own DNA sequencing technique, and I published it to Oxford Nanopore. Actually, the university, Yangnam University, helped me do that. And after that, I got a opportunity to go to Horten, their laboratory in Norway. It's a small scale laboratory in Norway, and I continued with my journey in high tech. But yeah, I do appreciate my foundation in classical mechanics, where you have oil rigs and really dirty engineering, extremely dirty and big structures. Dirty, when I mean dirty, I meant really like, I mean, if you look at high tech, it's all about clean rooms and keeping even to the nanometer range the how to say the surface has to be clean. However, in the oil industry overall, the energy industry, it's quite there's a lot of leniency over there. And I also actually was able to later on transfer to Siemens Gamesa in windmills because of my Indian Oil background over here. So overall, I think it was a little bit of a luck factor at the beginning that I clicked and they liked me as well. I was young, I was fresh, I was very, very, very eager to learn. I wasn't concerned at that point too much about climbing the corporate ladder or getting recognition. Whatever job they gave me, whatever they asked me to write, I would do a good job. And I was just a very disciplined person at that point, to be very honest, even now. So yeah, that's, I think, discipline and just showing up every day and doing the work. Yeah, helped me build a good journey. But in terms of you asked me how did the classical mechanics help me with nanotechnology. I think the overall experience with corporate in general helped me because it's not always about engineering is not always about knowing the physics behind it, knowing the mechanics behind it, but it's a lot about how do you talk to people? It's a lot about how do you put out your ideas and you persuade others on your ideas, and how do you make the other person listen to you in a meeting. So yeah, early experience, even when I was at 20 years and everything, at 20 years of age, that shaped me quite a bit as a person, and that helped me later on in different cultures, different corporate environments.
That is a really interesting story. You've talked about the V model with the rigor of design for Six Sigma. So for listeners who don't know about this model, so break down the V model to us like we are sitting at a bar.
I would love to. And then let me share my screen nicely. Then it's easier, then it's nicer. Let me go here.
All right.
Share my screen because this is very, very dear to my heart, the V model. Okay. Perfect, perfect, perfect. Then I'm going to, there you go. Yeah. So here you go. The V model with design for Six Sigma incorporated within it. If I talk about this model, well, it's a very, very dear thing to my heart. And I have now been able to help several different companies, well, incorporate it or at least make them aware of it. So for startups and scale ups who are thinking about how to make a organization-wide process that would help you connect your executive level decisions all the way to your suppliers and logistics and your warehouse level employees. I do believe that V model is a great process. What is it exactly? It's a product generation process. Whenever you have a extremely complicated product, extremely complicated, if you have an extremely complicated product, and for me, it's been windmills, it's been lithography machines, it's been medical equipment, like transmission electron microscope turned into a medical equipment. It has been several like big machines for me. And these big machines, they don't just come as one big structure. They have sub architectures and then sub architectures within it. That is, you have a machine, then you have a module inside, and then you have a machine. You have several modules inside of it, and each of these modules will have different components, and each of these components will have parts. So it's really an assembly of over assembly. Now, my language, be aware that whatever I'm speaking at this point, you would need a little bit of corporate experience to understand this. I can discuss this, I can simplify it and talk as if I'm talking to a high schooler. However, that will sort of remove and reduce the impact of this model. So I'm going to use technical terms and I'm going to use corporate terms. So what happens is that when you have an executive team somewhere, sitting in a boardroom, and they want to make money out of it. They want to make money out of the company. They want to, they see, okay, we have 5,000 something employees, or we have 50,000 something employees, and we want to grow to 100,000 employees, and we want to increase our share prices to so and so. Those are their higher level goals, right? What happens then? They would obviously translate those goals to managers, the people managers, and then the people managers will discuss with project managers perhaps, and then the information flow continues. One of the nice things about the V model is that the information should actually never dilute. So if you have a board level decision where you're talking about, oh, this time we have to release 20 machines, or let's say 10 machines of doing so and so. For the sake of an example, let's say a machine that will clean your shoe, right? Let's say a automatic shoe cleaner. I'm just giving an example. We want to make a product line of shoe cleaners, and we want to make 50 million in profits. These are high level expectations and high level goals. So for a long time, what has happened, and that's why people are also not very happy with corporate these days. For a long time, what has happened is that the executive committee says, we want to make this much of money, make it happen, do it for us. Obviously, that does not work, and that is not leadership. A true leadership is when you know how to take your desires and your ambitions towards the bottommost employee. And I don't mean bottommost as in that person is lower or higher, but I mean bottommost means the most detailed level employee, perhaps an operational employee working as a receptionist, or perhaps as an operation employee working in the production and making some stamps. So how do you translate your ideas sitting in your boardroom, wanting to make 50 million profits, selling a product line of shoe cleaners all the way to the operator? How do you do that? That's where the a process, this is one of the processes. A process like V model comes up. And you can also incorporate design for Six Sigma principles into the model. I'll come to that later on. First, let me tell you what is a V model. So first, what happens is that when you have these aspirations, 50 million euro profit, this much of cost reduction, this much of reduction in capex, this much of reduction in opex, and we need to also ensure that we have new customers and we are getting into new markets, things like that, your high level goals. The first thing you do is you give your ideas to your system designers and your system architects. And these people, they will not do much. They're not mechanical engineers or optical engineers or chemical engineers. They are system level people. They will simply draw the system. They will simply conceptualize it as a model. They might use things like MATLAB, etc. So it's called MBSE, model based system engineering. So they would use tools like that, and they would simply show how the system should work. If it's a shoe cleaning thingy, it should have it should have a spraying functionality. It should have a drying functionality. So things like that, in functions, in words, they would describe their system. So that's where your market demand insights, your end user insights, your high level goals on different aspects of your machine comes up. Then you have, from system level, you go towards a little bit on the specifications. You specify it broadly. So let's say you need a drying time. There is a wiping time and there is a drying time of a shoe cleaner. What are the specifications? So it should be 2 minutes plus minus zero point 0.1 plus minus 0.2, things like that. Those are specifications. Generally, this makes sense when you're working with capital equipment. But of course, a shoe cleaning thing is a very basic example I'm taking. So it's probably not making sense to many people here. But for you develop, after you make the concepts, you develop specifications and tolerances. After that, you make module and component level ideation. That is where mechanical engineering, electrical engineering, electronics engineering, industrialization, those people, they come into play. And each of these disciplines will give you their insights. And then the project manager or the system architect will bring all of them together and the structure is made. But each discipline will have to do their job by themselves. That's where you have your suppliers, tooling, and logistics as well coming into play. And then what you'd also do, so here you have the concept, you have specifications again for your disciplines, suppliers and tooling and warehouse and everything. But then this is where you actually make the product. And here you have your module and component level verification. So after you built it, you verify it. So how do you verify it? The specifications you get from this side. Then you go a little bit above and then you verify it in system integration level. And here, your verification specifications has to come from your system level requirements. Then after this, you verify it at the customer or your market insights in general. And how do you know what were the specifications? Well, those were the high level goals and the executive aspirations that were there in the boardroom. So this is the V model where every level of the organization is kept in loop, and we are not letting go of the primary goal set by the board level executives. So that is the V model in a very, very, very short, small nutshell. When I execute Design for Six Sigma into V model, it's simply, so Design for Six Sigma is such that when you make a product, the product should not function out of spec for a decimal of 10 to the power minus 6. So if it says that, if let's say the shoe drying time has to be 10 seconds, then for dryer that comes out of the assembly line really should be, the drying time should be 10.000000. So should not be 10.1, 10.2. So that's where the Six Sigma mentality comes. Is the extreme control over your finished products from your assembly line to the sixth of a decimal. So it's an extreme controlled product, and you have several different tools: Kano analysis, Pugh matrix, Triz. You have PERT, FEA, of course, and other tools. You have your design of experiments. You have your design FMEA. So you have different tools that you can use. And I have tried and I have been successful actually for many scale ups to incorporate the Design for Six Sigma tools into the V model. This is generally not done in larger organizations because it's simply extremely complicated. So you definitely need a consultant like me or somebody else to help you. And this particular thing, the V model incorporated with Design for Six Sigma, this is entirely yours truly. This is like not something you will find in any organization so far. But I know for sure that a lot of organizations, scale ups and startups and established organizations will benefit once you're able to incorporate Design for Six Sigma tools into all the levels of your organization, taking down the specifications, and you're making the product, and then you're also verifying the product. It really helps throughout the whole process. So this is very briefly your V model with Design for Six Sigma incorporated, very high level. And if you really want to know more, please contact me in my LinkedIn. I am known as Prachurya Bharadwaj over there. And you can also go to my website, www.thinkbuildscale.eu. And I would be very happy to go into the details of it. You definitely can look into my Spotify and YouTube podcasts as well. But I think this is best described one on one, where if you have your specific examples and your company products, I can properly describe how this organizational structure can take you to a whole different level as a company.
Interesting. That sounds like a really, really practical model. Yeah. So your work focuses on design for Six Sigma for mechanical system. Tell us, what's the most overlooked step when applying design for Six Sigma to complex hardware?
People often forget why they are doing something. It's funny, but they often forget what is the high level goal? What are you going to finally achieve? Because engineers are so deep into thought on, if you're an electrical engineer, you're so deep into thought on, I have to finish this, I have to do this, I can do this, I can do that, or I can make the product better by working on a whole different programming language, things like that. But you have to, people often forget the idea is not to work harder, but to work smarter in engineering and have more time for innovation as a company. If you work smarter and you do exactly what is needed to fill up the high level goals, then you are not spending your time on over engineering and over analyzing. And then you release the product sooner, and you have time for other things. You have time to go to a technology conference or some supplier visit and gain more knowledge and enjoy your time in the company. So that's what I see. They keep forgetting what is the goal. So sometimes if the goal is cost, so sometimes some projects, their goal would be cost reduction. So if you have a product, let's say your product is already built, right? And the management decides that we need to reduce the manufacturing cost of this product. If the goal is to reduce the manufacturing cost, then make sure that you're not adding more specifications, more tolerances, and more how to say more steps in the process. So this is what people don't understand, and they go ahead and they apply new physics, apply new ideas just because they're smart enough and they're intelligent and they want to do things. So that's often something where I see teams and project managers even derail. They go too much with the intelligence side of it. They go too much with what can we do? What can we do instead of what is exactly needed? So that's one thing I see.
So that's wonderful. You mentioned the Norwegian windmill blades that failed due to ice. So what's the most counterintuitive lesson from that occurrence?
The lesson from that one, for me at least, is never to underestimate nature. There were a lot of studies done. So I was the technical leader as well as the technical leader as well as I would say project coordinator of that project. And I was working for Siemens, but through another company. And my team was partly from Siemens, partly from Return AS in Norway in Fredrikstad. My team was, again, partly they were sitting in Denmark, in Aalborg. And then there were some suppliers as well who sort of became a part of the project. So it was a multidisciplinary, multi country, multi stakeholder, and multi-team project. Very wonderful. But one of the biggest things that happened there is that I was given a lot of historical information. I was told like, okay, these are the environmental conditions. We have done all the experiments. We have done all the tests. We know we have all the data. We have done all the feasibility studies, and these are the specifications. The temperature, the coatings have to survive these temperature ranges in the summer, in the winter, these seismic waves, and these are the biggest risks in the environmental conditions. And there was a big push, because it was funded by the government partly. So there was a big push from the government to get it done sooner. So because I had so much writing on it, and I had so many stakeholders in it. I studied the feasibility studies, and I read the reports, and I understood what they have done, and I just received I did not do further analysis on the specifications. I did not go further on, are you really sure you're giving me the right data? So things like that, I did not go that far because the timeline had to be maintained, and stakeholders had to be kept in alignment. And also, of course, there were concerns with finances as usual. And of course, my primary concern is the quality. Obviously, it's always the quality. So I was very much concerned with, okay, I have these specifications and I have to make the product according to that. But later on, I did understand that the failure, when it happened, I mean, well, initially that there was a failure already that had happened, and then the the windmill that the windmills that my project placing them was placing was deploying, sorry. um, they also met with some failures, but finally mine were okay. They're still running and they're still working. But the biggest issue was that the feasibility studies were not properly studied because of lack of time. One party did the feasibility studies and they said, okay, we have done so and so and so, we have done these and these and these tests, and according to our tests, these are the specifications. And then we come as the designing party, the manufacturing party who would continue with the work. And that is where the connection was lost. And this happens quite a bit on multinational corporations because they have several different teams in several different countries, and they all do their own thing. And a lot of the teams they rely heavily on suppliers. So it is, I think, very important that when a project manager or an architect starts in a project, no matter at what point he or she begins the project, proper research has to be done on what has been done earlier, and can you really believe in the earlier studies? And if you have even a little bit of doubt, the appropriate people should be brought into. They might say, oh, but they have left the company. Doesn't matter. You use your project management power, you use your power that you have at that point as a lead, and you bring in the right people. If this supplier cannot give you the answer, find another one who can give you the answer. Nobody can give you the answer, then send out an investigation team. Tell the project manager or tell the executive committee that I need a investigation team to actually go and make sure that the feasibility studies are really correct, and at least for the sake of this project, new experiments or new tests should be done, especially for something so severe like windmills or a lithography machine or a medical equipment, right? These are severe things. These are not just your simple injection molded plastic components. They are real engineering. Even if there is no doubt, even if you are completely certain that the feasibility studies, etc., the work done before you is perfect, you still should continue with making your own opinion about it and receive the data that you want to receive, that you should have for your project. And it's easy to say it out in a podcast, but there is absolutely no time in a project management environment, in a so I'm a person of technology, so I'm telling you we should have time to look at the data. We should have time to look at the feasibility studies, time to look at the simulations properly, time to look at what boundary conditions they use there. So I'm telling you because I have the knowledge, because I know where things can go wrong. But there are people who are taking higher level decisions, and they do not exactly have the knowledge to pursue that manner of thinking. And therefore, it's so important that people who have engineering degrees, who have been in different companies, they understand and they speak up and they place their opinions. With that, I also do have to say you are fine to place your opinions, and it's okay for you to warn the project manager or warn the lead or warn even the executive committee. However, the burden should not you should not feel like it is your burden. It's enough for you as a young engineer or as a meteor engineer to simply mention the risks to the other party. But you don't have to burn yourself out. You don't have to take things personally and make it very determined. Like, you don't have to go too far. The reason being for your own safety. You have to make sure that your health is fine. And this is one of the biggest causes of burnout amongst young engineers, that they see all the risks, they see all the problems, and then they really go after solving everything. But sometimes it's also important to place your fears and your concerns properly in an email or in a meeting and let it be. The right people, if they're smart enough, the right people will hear it. The right people will take the right decisions. If you feel you can bring it up in different meetings every day, but then immediately you should detach yourself and you should continue working in your sphere of influence. This is only for your protection, what I'm saying.
That's wonderful. So you worked as an optomechanical engineer at ASML. Tell us what a normal day looks like working as an optomechanical engineer.
I was an optomechanical engineer and also an architect, so mostly an architect over there. How does it look like? A lot of firefighting. So, in okay, be aware that ASML is a whole different beast. ASML is a company that releases world's most complicated machines for the world of semiconductors, but in general for the whole world. They release the most complicated machines in the world. So ASML, how I work, how my day would look like, it doesn't mean that it would be the same for if I work in Siemens or if I work somewhere else in a startup or if I just start my own company. Everything will be different. The title might be the same, the day might be different. For me, there were just a lot of discussions and meetings with product owners and scrum masters and uh, different architects from various different disciplines. So the V model I showed you just now, I was just going all over it. I was talking to people from all over, from systems to module to component suppliers, all the way to integration and then system integration and then finally the customers. So I was going throughout the entire because I was an architect. If I had been only an engineer, then my work would be a bit different. My work would be designing in CAD, a lot of CAD design, computer aided design, and discussions with optical engineers. So the optical engineers would make the optics design, which is your ray tracing, etc., on how the rays will hit different lenses and mirrors, and then finally would converge or diverge and form the image. That's your optical design. And then finally, and you as an optomechanical engineer, you would have to make mounts and frames out of it. So a lot of discussions on understanding how big it should it be, which kind of material should it be, what is the thermal expansion needed, etc. So lot of thinking about the physics behind it and thinking, and at the same time, as an engineer, interestingly, you will need a lot of inputs from architects like me. You will need to know what the system does, and based on that, you will need to make your CAD. And then I might, as an architect, I'm always there to say, no, sorry, this is not going to work. Sorry, you have done a great job, but let's tweak it up. Let's make it 2 centimeters shorter. So that's where there's a lot of discussions and a lot of push and pull. However, to be very honest, here is also another piece of advice for the young generation, that when you're working in an engineering environment, often what I see is people make everything too personal. They make everything, if somebody is saying this is not going to work, they make it, oh, why will it not work? I've worked 20 hours or 20 days on it, and you're telling me now, things like that, right? So it becomes personal, it becomes emotional really quick. So my piece of advice to everyone, senior, media, junior engineers and architects, would be, please, please, please detach yourself from all of this, because the higher you scale in the corporate ladder, the more you understand that nothing is clear. The more you understand, and that's why I always suggest the V model to scale ups. Nothing is clear. To the executive committee wants to do something. The system engineer wants to do something, but I am not receiving the right information, what they want to do. They will give me some documents, but I might not have the time, and the documents might not contain everything that I need. So it's a lot of information that is missing, and information that is floating around here and there. And as an architect, it's all about how do you make sense of the floating pieces of information. And as an engineer, it's all about how do you make that information concrete? That is, you make the design, you make sure you do all the calculation for the tolerances and specifications. You basically help out the architect as much as possible. Because the architect is going to go, architect or the team lead or the technical lead will be handling, generally they will be handling 20 or 15 projects at the same time, and will be managing 500 different stakeholders in different countries. And they do not have the time to sit with you and help you with each and every line that you draw. Or each and every circle you make. So some of these things you have to just be patient that, okay, let me do it this way and then we see. Or we have done it so and so way in another project. Let's just work it out. So that is, so answer your question, Ezekiel. Did I really? Okay.
Yeah, you did wonderfully. Yeah. So I like to ask, what's the importance of ASML's machines in today's technological uh, constraints? We now have computers with several times more processing power than in the past decade, and graphics processors that aid AI and machine learning advancement. So, what has ASML got to do with these?
So what you just mentioned, your microprocessors and your data centers and your LLMs, etc. They all need something called. They will need semiconductor chips. They will need transmitters and transducers, diodes, etc., etc. They will need those. What does ASML machines do? ASML machines work with they automize a process called photolithography. And photolithography is just one process where you are developing a part of the transducers. And you actually have several different layers and layers of the system of the chip. To explain what ASML does in general, let me just explain the photolithography system. So if you have a wafer over here, and what is a wafer? Let me show the wafer in semiconductor. This one is a wafer in semiconductor. These are they are the basis for developing your electronics, your phone, your camera systems, your electric car, your smart homes, any smart machines out there, or any machine out there nowadays, they're all built using wafers. Wafers have patterns in them. You can see these kind of patterns. They have patterns in them, and each of these patterns could be around 10 nanometer to 2 nanometer small, and they could be stacked on top of each other. I could just see for. It's okay. I think maybe just not, I wouldn't go here because I'll just keep it a bit simple. Okay, I'll just keep it simple. So if you see here, ASML, how the photolithography system works in general. Don't worry about ASML, just think about how the photolithography system works. You have a light source, you have a photomask, and then you have a projection lens, and then you have the wafer over here. What happens with the wafer is that you have different photoresists. Some of these resists, there are positive photoresists, and then there are negative photoresists. Some of these photoresists, they work in such a way that if it's a positive one, they work in such a way that the light source, when it hits the resist, it will solidify. And the negative one will work in the opposite way, where when the light source hits it, then it does not solidify, it actually dwindles away, and then you wash it off. So based on that principle, it's called photolithography. Lithography is nothing but writing in stone, and silicon is stone, as we all know, in layman terms. So you just use photoresists and you make various different structures, very, very small and intricate structures on your silicon wafer. And that is the basis of your transducers and transmitters. Um, Also for many other chip components over there. So what does ASML photolithography machines do? If you look here, this is, if I'm not wrong, this is for EUV lithography. This is the older EUV one. So they actually, if you see the source over here, they have different projection lenses over here, and the rays are bent in such a way that it really is narrowed down and it hits the wafer over here. If you look at why ASML's EUV lithography is important for semiconductors in general, they are developed world's most complicated machines for photolithography, and I described the process a few minutes earlier. There is no other company. There are some attempts by Canon and Nikon at this point, but currently there are no other companies that are able to produce 2 nanometer scale of transducer structures on your silicon wafers. At the same time, there are the older machines of ASML, the older machines of photolithography machines of ASML are also quite popular and quite good. And the fabs, the fabrication facilities of Intel and TSMC, those big players, they have a lot of ASML machines, and their engineers are very much used to ASML machines, and that's why ASML has a complete monopoly over the semiconductor equipment for photolithography equipment market. To give you an idea, the UV machines, the latest, biggest ones, are around 1,100 cubic meters big. So they're big machines, they're huge machines. And yeah, that's only the beginning. Gradually, I hope that ASML also releases newer machines, and I hope that company continues growing. And I hope it also goes further than photolithography, automizing the photolithography process. But in general, ASML's importance is that it forms the machines of ASML forms the basis of transducers and the overall electronic structure of your electronics, the overall system of your electronics. So few years ago, when you were during Corona times, there were problems with there were actually problems with chip shortage. There were problems with electronics being released. So a lot of electric vehicles were not released in Europe, or they didn't just make it. One of the biggest reasons is actually that US had made some sanctions, and because of that, it was difficult for the machines to be sent over to certain areas of the world. So that's how big of an impact ASML machines have in the world of data and semiconductors in general. I can go on and on about it, but yeah, for now, this is it.
That's a very detailed and wonderful explanation you just gave us right there. Well, yeah, yeah, that's really valuable. So, you have experience in computational mechanics, including finite element analysis and computational fluid dynamics. So, what's one common mistakes that engineers make when trying to interpret simulation results and apply them to real-world problem solving?
Most of the people I know, um, they don't make these mistakes anymore. Most of them don't make these mistakes anymore. People who I know who make these mistakes are younger generation or a bit in the graduate level, if I might say that, if I can be a bit bold on that. I think the bigger thing is simulation is simulation and tests are tests. However, real life data is real life data. So these are three different things, and they should never be used instead of each other. They should never be replacing each other. Never. Doesn't matter how big of a computational scientist you are, doesn't matter how big of a processing capacity you have in your computer, doesn't matter if you have given lectures in different universities about your the model that you made, but it's a simulation. Simple. It's a simulation. There's a lot of fun in it. There's a lot of fun in it. You really when you're doing the work and you see the results come in, you enjoy it. But it should always be expecting. Like it should always be as per your expectations, in the sense that you should have a little bit of idea on. You should do some hand calculations first and find out that okay, the fracture point is around here, the material will yield around here, the structure, the thermal conductivity will stop the heat at around here, and this will be fine. So that comes from experience, to be very honest, and it's not that simple. So that's what I'm saying. The mistakes that I saw are not from the people that I talk to every day, but from very fresh graduates or people who just have stayed in simulation for years and years and years, and they never really went into product development or manufacturing or project management. So you have those people as well, which is amazing. Again, they're all experts in their field. So I think the neglect of hand calculation is one thing I see often. And at the same time, I also see sometimes that some people who are a bit in a different generation, a bit generation above me, to be honest, they are too reliant on the hand calculations. It is their benchmark. But many of the finite element models, if you use COMSOL and ANSYS, COMSOL especially is my favorite, if you use those kind of softwares, you're definitely going beyond hand calculations. So here is where your experience comes into play, where you understand that, okay, um, I am expecting this kind of a result. And then you have to, using your hand calculation, but then you have to think, okay, but what happened in the field exactly? In 1982, this thing happened. This seismic wave came up. So things like that, you will have to look at the history and you will have to go deeper into the operational conditions of the machine or the final product. And you have to to say interpolate your results, and you will have to bridge that gap, and that is why it's very important. So here's the thing: simulations are very intensive, very labor intensive, and it's very numerical, right? So the experts who are working in simulations, they are set in their ways and they will do their thing, and they're in a nice vertical growth trajectory. They're growing. They're going deeper and deeper and deeper into their machine and their software, and they know all the tools and the methods of that software. However, architects like me and project managers or product development engineers, we have to go to the simulation experts and we have to sort of help them understand that I need it differently or I have new knowledge for you. And based on that, they will have to change their boundary conditions, or they will have to change their load. They might even have to change their mesh. They might have to change different things. Or what I do, my favorite is build a matrix of different load conditions and different boundary conditions, and show how so and so combination will give you this result, so and so combination will give you this result. So there are materials, there are boundary conditions, there are load conditions, there are um, uh, 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 how to say, there are different conditions that need to be looked at separately and at the same time looked at all together. And looked at all together, you have only specific softwares. There are specific softwares who will help you look at multi-body simulation, multidisciplinary simulation altogether. So that's where you will have to sort of, that's where, the maturity comes into play. Your corporate experience comes into play. Exactly, Ezekiel, what you asked me, how did my Indian oil background help me with nanotechnology and semiconductors and high tech? This is exactly what it is. I mean, I already learned the value of collaboration, the value of sitting together with people, and value of listening to them, and then do the work and not get annoyed if they change their mind, and not get annoyed if they say that, we needed so and so, but you only did so and so. So things like that. It's all about collaboration and communication. Nothing is personal in corporate. Nothing is set in stone. Everything can be changed in engineering, and you just have to learn to go along with the flow. Easy to say, very difficult to practice when you're in it, when you're really in the zone. So yeah, that's in a nutshell. How do you deal with simulations? Biggest mistake, Ezekiel, that I've seen is over reliant on no communication. There is no communication between what are the real operating conditions versus what were the hand calculation versus what the simulations do. Because I also do not agree to some of my seniors who are overly reliant on hand calculations. So if you're so reliant on hand calculations, why are you asking me and my engineers to do the work of simulations? Go and figure it out on your own, right? I wouldn't like it. I would like, no, your hand calculation is good, fine, we know our software, and we have gone into the details on how do we change each boundary conditions and how do we go into the meshing. My favorite, as I already mentioned, is COMSOL, and you can really play with the physics as much as you can. You can go deeper. COMSOL is nothing but written on C++. You can go deeper into the codes of the software, and you can figure out why this mesh acts in this way, or why making it how to say, making it thermally conductive more acts this way. So those answers are also there. So the deeper you know about the physics behind the phenomena, the physics behind the simulation, the better your simulation is. It's never the complete answer. It's never the complete answer, but at least you will be able to know what are the limitations of your model and what are the capabilities of your model, and that is able to educate your stakeholders better. Did I answer correctly, or did I answer
You
clearly?
you sure did answer it like perfectly. You know, I being someone who recently worked on projects using simulation tools from finite element analysis, computational fluid dynamics, and even topology optimization on the other undergraduate level. I think I can very much relate to these mistakes you pointed out. And yeah, I learned a whole lot from what you just talked about here because while working on these projects, then would over rely on just the simulation tool and the simulation result we get from it. And we don't really like uh, focus our attention on some manual calculations or physical testing. And I guess I think I actually relate to what you just how you just break that down for me. Yeah. So and I hope this also helps. I mean, people like me in the undergraduate level or who just started their career journey to understand. Yeah. So thanks for that.
Absolutely. But if I can give an advice here to the people in at your stage in life, um, simulation. You can please go towards simulation and look, but you have to see yourself as a simulation engineer. Are you really a simulation engineer? Are you really meant? Because if you take your career towards simulations, then you have to be very good with the software that you have. You have to take one software, NX Nastran, NX Simulation, COMSOL, ANSYS, flow beams. There are different types. So you have to take one software, and you cannot do both FEA and CFD. You can do at the beginning of your career, but later on down the line, you would really have to specialize. You can do it, but you have to really understand, are you a person who is a vertically growing person? That is, that you only learn one thing and you make it, you keep learning, 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 learning. Are you that? Or are you a person who is a bit of a horizontal person? Because I am most certainly this. Hello, I am this, and every year I am growing. I'm growing
Great.
every year, every month. So are you that, or are you someone who's growing vertically and learning? I'm not saying they are good, bad. I'm not saying it's one is better than the other. That's not what I'm saying. But I'm saying, what is your core personality? Are you happy? And you can make money. If it's about money, you can make money in both. Engineering is always well paid, so you can make money in both directions. But are you a person who is happy learning one thing and then being really nicely an expert on it? Are you that? Or do you want to know a lot and then you want to manage things? So I have to tell that. I really wished somebody had told that to me when I was at your stage, Ezekiel. And then things would have been easier for me, because for a long time I tried to make myself an expert, which didn't work. Simulation, on the other hand, I'll also have to say that you can. So again, the operating conditions, proper data from operating conditions, the hand calculations and simulation have to go together. They really have to go together. They cannot be one or the other. So I'm also not happy with my seniors, some of my seniors telling me, seniors in the sense not in position, but in experience, they would tell me that hand calculation is superior. I say no, because I know my software. I know each and every detail about the model, but the hand calculation is only a simplified load, a simplified version of it. It's a block model. We literally call it the block model. You're not taking into account the topology. You're not taking into account the geometry of it. You're not taking into account, you cannot take into account the material behind it. There's so many things in hand calculations that you cannot understand. But when you go deeper, when you really, really know the software, you have to know. It's not about winning an argument with somebody, but you really have to know your simulation model. And when you really, really have the answers, why this is happening, why that is happening, then that's it. That is what you need to have a holistic picture. But again, that's where your personality comes into being. Are you a person who is happy learning a little bit more than your simulation and your model? Or are you a person who only wants to work with the software? Because either way, the project will continue. Somebody will come up and somebody will stop the project or the product at some point. Anyway, it's going to continue. So that's my tip, is really to have operating conditions data, hand calculations, and simulations. All three of them should go hand in hand, and a simulation engineer should have adequate knowledge of all three of them. If he or she doesn't have the knowledge, then he or she needs to ask for the knowledge and ask proof of the knowledge as well. So that's my final take on the simulation part.
Interesting. That's a really, really wonderful illustration there. I really must commend it. So, one more thing before we move away from simulation. So, with the advent of AI and machine learning, so what's your opinion on the future of simulations and computational mechanical mechanics tools like FEA and CFD?
like them. I don't see a hindrance. I like it. I think LLMs will make it easier for at least to use software. And in many cases, Ezekiel, if you see how LLMs work and how a programmed software like Comsol or ANSYS work, it's quite similar. The LLMs, your usual AI models that you see, ChatGPT, Gemini, whatever, they are more in a user-friendly format. They are for the common people who would say, hey, can you help me write an essay on why dogs are beautiful? Basically, we are doing the same thing when it comes to simulation. I would say that simulations are also LLMs. The user simply has to have more control over the input and the output. That's one thing. And the second thing is, I think using LLMs, incorporating LLMs into something like Comsol, I think that will enhance because I think then the software might be able to you might be able to ask the software, I want to achieve so and so and so, what do you need for that? So you might be able to talk to the software and you might be able to grow together, to be very honest. So I do see a good future for LLMs incorporated within the simulation softwares. I'm not against it at all, and the world is moving in that direction, and we should, but it should not replace human understanding. Again, what I said, the simulation expert has to know operating conditions, hand calculations, and simulation results, all of them, all at once. He or she has to know, he or she has to have the knowledge behind them. So that part, as long as you have that part, use as many LLMs as you want, incorporate it and take help of it and learn and make your life easier. And of course, like I said, if you don't over engineer stuff and you make your life easier, you get to do more fun stuff. You get to spend more time on innovation. You get to spend more time on ideas and concepts, right? So I'm definitely for it.
Great. So, you work as fractional CTO at Think Build Scale. So tell us what Think Build Scale is about. What's like the first question that you would ask when auditing a failing mechanical system?
While I'm auditing, okay. Um, well, okay. Think, Build, Scale. It's a podcast as well as a consultancy service, and it's tailored towards capital equipment industry. I join as a fractional leader. I could join your scale up or startup as a fractional CTO, or I could join as a consultant, or I could join as a system architect, mechanical system architect. I could join as any of the leadership position where you think you need me for that particular task. Personally, I do prefer to be in the fractional CTO mode because then I'm able to really see the overall organization and help you, like I showed in the V model. You have your executive decisions and then come all the way towards building and then verify and go through customer. So I would personally like to be there, but at the same time, this consultancy, I'm just open for various different levels of fractional leadership because I can make an impact in various different manner. Like I said, I grow horizontal. In terms of what are the problems I see when I'm auditing, so what happens is that before I start my work, I would audit the company. I would find out where the problems lie. And again, like I said, my personal preference is always to be a fractional CTO, and then I can look at the whole organization. But sometimes, if that's not possible and I have to start as a system architect, then I would also try and look at the things that are within my scope. What are the things what are the mistakes I find in companies during my audit? Most of these mistakes are actually not from the organization. I find the mistakes in miscommunication, and that is actually from suppliers. In capital equipment or in almost any production related environment, you're always relying on suppliers and suppliers. And oftentimes suppliers might be in another country. They might be in a different continent. They might speak a whole different language, like technical language as well as a whole different language. So because of that, there are many miscommunications happening. Roles might not be clear. So they might be under the impression that they only need to deliver a component, but at the end of the day you find them interesting, it clicks, so you also give them the entire module to work with. So based on that, they will make their investments and they will start working on it, right? And then some miscommunication will happen, and then the specifications are not met because, like I said earlier, that the earlier example I gave from Siemens is that the company wants to, like most corporates want to save. They want to save money as usual, but and that's fine. So there will be different suppliers, and generally, a lower cost supplier is preferred, and there are many other factors behind it. What happens is when you have, let's say, one complex system, but you have several different suppliers working in different modules, etc., or different components, the tolerances are different. Documents that have gone to them are different. The documents might be older and the newer ones have not been updated. So it's always a miscommunication. It's always, at the end of the day, you can make processes after processes after processes, but then people might not follow the process and people might just complicate things. So that is something I find to be the biggest. Um, um, but other than that, if you look at practical issue, I think the second biggest problem I find within the company is lack of training. The engineers are not always trained enough for the product that they're building. And the third kind I have found is actually just lack of documentation. That exact same thing I mentioned about the Siemens problem, that some feasibility studies were done some years ago and you are using the specifications from that feasibility study, but you don't know why. So the question of, when it comes to the question of saving money or increasing the quality, then you're changing the product. But when you're changing the product, then you have to really know, why have you made it in such a way? And then oftentimes there are no answers. So a lot of times companies, bigger companies as well as smaller ones, they do not know enough about their own product. It's really strange. They don't know enough about their own product. And that's because of a lack of documentation. That's because of a lack of, like, just overall knowledge. Like, people come and go, and companies also treat them replaceable. They're like, okay, if you're gone, we will hire someone else. But it's not about hiring someone else. It's about keeping the knowledge, the flow of knowledge within the company. So that these are the things that's something I see. So yes, oftentimes I'm hired or I'm consulted for for certain technical problems that I have to solve. But at the end of the day, the really root cause of the problem is not really technical. The root cause of the problem is human interactions. But I can give you one thing also I have seen, that a lot of the decisions that are made long time ago, and the decisions are never questioned, they were made to save cost and to save time. If you look deeper and if you ask, why is this cup made in, it's a very, very, very high level, silly example, but why is this cup made in this manner and why not in a different manner? Because if you make it square or something, it's just going to cost you more money. It's just going to cost you more time to go and shape it in that manner. So just make it cylindrical and put some paint on it and sell it to people. Put a nice brand, sell it to people. That's how it's done in corporate. So you have to go deeper into where the exact decision was holding the project back. Sometimes the decision is simply a lack of knowledge on why things have been done the way they have been done. And because the knowledge is not there, to change anything takes a lot of time, because nobody wants to take the risk of changing it. Quite a beautiful world, the world of corporate. And yet it's lovely to be a consultant, to go hand in hand with your clients and to make their lives better.
That is wonderful. So finally, There's one more question I have for you. So I personally like to save this one for the last to ask every guest that come on this podcast. So tell us, what does innovation mean to you and how does it relate to your field? I mean, earlier in this conversation, you said something about how engineers need to work smarter, so they have more time to innovate. So, I mean, tell us what it means to you.
Innovation to me, that's very philosophical. Innovation to me is being able to play with your mind, being able to come up with solutions that do not exist. Instead of whining and saying that I don't have this, I don't have that, you just make your own path. You just make your own machines. You just make your own processes. So that is innovation for me in simple terms. But if you look at corporate in general, innovation in corporate environment is the ability to have a competitive edge over your competitors and to maintain that competitive edge. I disagree when people say nobody wants to come second. I disagree when people say you have to go to the market first. I disagree on that. I say you have to go to the market as the one and only. You should go to the market as the only people who can do this. And nobody can do it. Of course, there will be people who will try to reverse engineer and try to follow follow your method, follow your model. But knowledge, after all, wins, right? Knowledge is everything. And if you have the knowledge, your company has the knowledge on how to make it work and how to continue perfecting it, because that's also innovation. It shouldn't stop. It really shouldn't stop. It should continue to be perfected. So come up with an idea that is exclusive and unique, and not just for the sake of it, but come up with an idea that is exclusive and unique, that really truly stems from you and you're solving a problem, you're disrupting the market, and continue perfecting that idea. Yes, you can release different models in the market, but the goal should not be to go there first. I really disagree on that, because project managers generally are like that. You have to get to the market first. Why? What are you going to do by being there in the market? In fact, you should not be the first one, because if you go and be the first one, the only thing you do is you're just you're making the audience, you're conditioning the audience to conditioning the customers to use that product. But then will see what mistakes you have done, and they will just do it 1,000 times better than you. They will reinvent it 1,000 times better than you, and then they will. And that's exactly what happened to Facebook and MySpace. MySpace came first, but Facebook perfected it, made it better, made it more relatable. It's as simple. It's very simple. So I don't believe in going somewhere first. I believe in innovating something so extraordinary, exactly what ASML did. Something so extraordinary and so unique that only you can do, and you have the knowledge, and you keep your engineers and you keep your workforce happy so that they can stay in the company, and you are the only one who can touch it, and nobody can touch it. Knowledge is everything, everything, especially in this world of LLMs and everything and all, where yeah. So that would be my take. Innovation is about just absolutely disrupting the way how things have been done, how things have always been done. Just disrupt it and do only and come up with something new. At the same time, exactly what I'm saying, that what I said, there are people who will go vertical, um, and people who will go horizontal. So generally these horizontal people, because they can collect experiences from various different fields, they are able to do these disruptive and innovative things. Again, I'm saying not everyone has to go there, but to answer the question on what does innovation mean for me? For me, it's that. It's not about getting somewhere fast and first. I don't care about being the first. I care about being extraordinary. I care about being the one and only. I care about being the everything, making my own universe. That's innovation for me.
That's wonderful. So, finally, I know you said something on this earlier, but I'd like you to say it again. So, tell me, where can listeners contact you to learn more about your work on design for Six Sigma or your Think Build skill?
Yeah. So you can go to my website, www.thinkbuildscale.eu. There are different episodes I made on examples of various different capital equipment. And so you can listen to them if you're in a podcast listening mode and you're driving somewhere and you have time, and you can listen to my podcasts. I have not been releasing episodes quite often, and my podcast is not like yours, Ezekiel. It's not. I don't have guests over. It's just me. I talk. um, so you can start with that. Or you can just go to LinkedIn and contact me there. Literally, my name, Prachurya Bharadwaj. You will find me in LinkedIn. I think if you just type my name, I will be the first one to pop up, and connect with me, and we will talk. Who can connect with me? That's an important question. So if you are someone who's building a capital equipment, what is a capital equipment? It's an equipment, it's a product which increases value over time. Your PC, for example, it's not a capital equipment because it will depreciate value over time. Your car is not a capital equipment. It will depreciate value over time. However, if you make a medical equipment, if you make a surgical robot, if you make a different kind of transmission electron microscope, if you make a data center automation platform, these are capital equipment because you can, as your company progresses, as the growth of the company progresses, the equipment becomes more and more valuable. So that is capital equipment. So there are few selected industries, companies in the world, but I hope that more startups and scale-ups come up with it. And even if it's not capital equipment, we can still have a cup of coffee. We can still talk and get together. And if you have a simpler product which has mechanical engineering functionality in it, definitely contact me. Definitely seek my advice if you want for manufacturing, for designing simulations, as we discussed, figuring out who your supplier base should be, your whole supply chain, etc. How do you organize it in such a way that the high level goals are not diluted when it comes to details? So things like that, we can definitely have a talk and see where and how I can be of service to you. So just remember that Think Build Scale is a very boutique consultancy company. Everything is tailored to what you seek. And a lot of my projects are actually a bit confidential. I have confidentiality agreements with them, and I don't take the names of my clients in public. I would never do it. So be aware that my public image has, you don't have to worry about your data and your information to be out there for the world. So yeah, find me in LinkedIn. You can also find me in Spotify, YouTube, but the best is LinkedIn, I would say. The best is LinkedIn. My email address is very simple. It's actually all over my podcasts. It's Prachurya, my name, Prachurya .b @outlook.com. So that's about it. It's there are many ways to get to me.
All right, Prachurya, it's been a really awesome conversation with you, and I'm really honored to have you on the show today.
Absolutely, Ezekiel.